Bright Tuty. Every student matters.
There are a few characteristics of sound waves. They are very important. Let us try to relate. Characteristics of a sound wave. Now we have seen this is a kind of sound wave. Let us try to relate. We have made this sound wave like this. Okay, this is a kind of sound wave. This particular line we called it, this is the line of normal density, where the density of particles was normal, neutral. Alright, now this we called as compression. This is the rarefaction, compression, rarefaction. We already know what compression and rarefaction are. Compression are the density above normal when the particles are compressed, and rarefaction are the areas where the density is less than the normal, that is the particles are a bit apart from each other. And we also call it a region of higher pressure, that is compression, because the particles are closer, pressure exerted will be more, and rarefaction region of lower pressure. This all we have studied earlier. We will be talking a bit ahead of that. Now first of all, let us try to get some alphabetic representations of these points. Let us give these points the alphabetic representations of A, B, C, D. Again this is E, I will give it F, this is G, this can be H, I, and so on. Clear? Now when we will be talking about the characteristics, we need to remember what we have drawn here. We will talk about the characteristics one by one. Now the first important characteristic of a sound wave is its wavelength. Now what exactly is wavelength? When we define wavelength, we say that wavelength is the minimum distance in which a sound repeats itself. It is the minimum distance after which the sound wave is repeating itself. Now what does it mean by saying so? Let us see with the help of this figure. Let us say that this sound wave starts from A, right? After having one compression, that is high pressure, and then undergoing rarefaction, when it completes one oscillation or when it reaches this point E, we see that from E it again starts the same process of the same path of the part which it has started from A. So I can say that from E now the wave is repeating itself as it was doing from A. So this minimum distance from A to E, this will be known as the wavelength of this wave. It is not necessary to take it from A, that is why we have put up all these alphabetical points. Now let us take from B. If I talk the wave taking this point B as a starting point, from B it went down, then again undergoing the rarefaction, it came up to the line of normal density and it came up to point F. Now if we can observe, it is quite obvious that from B the path was taken along by this wave and the same continuation will happen from C. So I can say that from B to C this distance is also wavelength. Similarly, if I talk about C, then I can relate from C to G, it will be wavelength, because one rarefaction, one compression coming to this particular point G, after that again it will carry on with the same path. So from C to G it will again be wavelength, right? So wavelength is the minimum distance, that is one complete compression and one complete rarefaction, that is known as the wavelength. And since we are talking wavelength in terms of the distance, the minimum distance after which a wave repeats itself, therefore the SI unit of wavelength is meter, which is represented by small m. Now this wavelength is denoted or represented or expressed as this sign. This we can call it to be just opposite y, and this sign is known as or called as lambda. The name of the symbol is lambda, right? Fine. The upside down y, that is known as lambda, and this is the representation of wavelength. So this is how we will represent wavelength, with lambda. So what is wavelength? Wavelength is basically the minimum distance after which this particular wave is repeating itself, right? One complete compression and one complete rarefaction, this distance is known as wavelength. Now we can relate that the one complete compression and one complete rarefaction is equal. So we can also say that one complete compression, the distance AC, is actually half of AE. That means one complete compression is basically half of wavelength. One complete rarefaction is half of wavelength always. Clear? Fine. So this was the first characteristic, that is wavelength. Along with SI unit, you need to remember, you need to recall and remember its definition. Now let us see the second characteristic. The second characteristic of a sound wave is the amplitude. Now what exactly is the amplitude? We have seen that the density of a particular wave varies. In the case of rarefaction, the density is more because the particles are closer to each other, and in the case of rarefaction, the density is less. I repeat, in the case of compression, the density of particles is more and the rarefaction has lesser density as compared to the normal density, right? So the maximum displacement, this particular height to which this wave is moving from the line of normal density, whether it is above this line or below this line, this particular height we can say, or the maximum displacement, is known as the amplitude of this particular wave. And since the amplitude is the displacement, again the SI unit will be meter. That will be represented by small m. Fine. This is the amplitude of a particular sound wave. Clear? So this is, we can relate it to be, if I take the point x, so this will be bx, and if I take y or cy, or I can say if this point is z, then dz. This is the amplitude. Clear? Let us come to the third characteristic of sound wave, and that characteristic is time period. What is time period? Now the time period is the time taken for completing one full oscillation, means one full compression and rarefaction. So the time taken by this wave to complete one full oscillation, right, that is known as the time period. Time period is expressed as capital T, and this time period, of course we are talking about time, so there are no two facts, that the SI unit will be second, represented by small s. Got it? Fine. The fourth characteristic is the frequency. Now this is very important to understand. What is frequency? Frequency means how frequently the sound waves or the activity is being performed. For example, I am beating a drum, right? So how fast, how frequently I am beating the drum and producing the sound, that will be the frequency. That is the number of times a particular event is happening place. And since we are talking about in terms of waves, so we will say it will be the number of waves produced in per unit time, and the unit of time is second. So we can say frequency is the number of waves produced in 1 second. How many waves are produced in 1 second? That is known as the frequency of waves. This frequency is represented by this alphabet. This is known as, this is Greek representation, and it is termed or called as nu, right? This frequency, for the sake of convenience, we can relate it with small f also. That is also acceptable, not a problem. Got it? And very, very, very important, the SI unit of frequency is hertz, which is represented by Hz. Fine. This is the SI unit of hertz. This is the one marker. Many times it is asked, what is the SI unit of frequency? That is hertz, right? So we measure frequency in terms of hertz, and frequency means the number of waves produced or the number of cycles completed by a wave in 1 second, right? Fine. Okay, now if we try to relate the time period and frequency, very important thing is, what was time period? Time period was the time taken for one complete wave. That is known as the time period. And the frequency is how many waves or how many cycles in 1 second. Got it? So if we try to relate, they are actually opposite to each other, and this is very important, that frequency small f or nu with which we are relating, this is equal to the reciprocal of time period. Nu is equal to 1 by t, or f is equal to 1 by t. It is opposite to each other. Clear? Fine. So these are the 4 characteristics relating to it. Let us see now the last one, which is the speed or the velocity of a wave. Speed or velocity means the speed at which a wave is propagating in any particular medium, if it is longitudinal. Okay, if it is transverse, it can be in vacuum also, but the speed with which a wave is propagating or traveling. Now the formula for speed and velocity: for speed, as we all know, is speed is equal to distance upon time, right? Now when we talk about the distance in terms of waves, we relate this distance in terms of wavelength, as we have studied earlier, divided by time. So I can write speed is equal to wavelength upon time. This may also be represented as speed, we represented with small v. Wavelength, we have seen the representation to be lambda upon t. Got it? So this is the speed of wave, which is calculated by this formula: speed is equal to wavelength upon time. Now just above we have studied that frequency, or f or nu, whatever we take to represent it, that is equal to 1 upon t. Now if I take the reciprocal of time period to be frequency, so this equation could have possibly also be written as wavelength into 1 upon t, and replacing 1 upon t with frequency, I will get the velocity is equal to lambda into frequency, which can also be represented as v is equal to lambda into nu. This equation is very, very, very important, and this equation is known as wave equation. You will be studying a bit of detail regarding this wave equation in higher classes, but here also in 9th class you will get a few numericals to be solved because of this formula that we will be using. This is wave equation. We are also asked to derive this wave equation, which is quite simple. We will start simply with the speed of a wave, which is equal to distance upon time. We need to specify that the distance of a wave is expressed in terms of wavelength. Then in that case we can represent it as speed is equal to wavelength upon time, or we can write it as lambda into 1 by t. Next, we know that frequency is reciprocal of time period. So, putting or replacing the value of time period with frequency, we will get V is equal to lambda f, or V is equal to lambda into nu, or speed is equal to wavelength into frequency. This is our wave equation. So, these are our characteristics of sound waves. Okay. So, looking at the wave equation, we see that the speed or velocity of wave is the product of the wavelength and the frequency. Sound in the form of wave is the loudness of the sound. Now, what exactly is meant by the loudness? That means how much loud the sound is. Loudness basically refers to the amplitude. It refers to the volume at which we are listening to the sound, right? And this loudness, it depends, we need to remember on which it depends. It depends on the amplitude of the sound wave. Now, this is very important. We need to remember that loudness depends on amplitude, or the amplitude of the sound wave will determine the loudness. Let us try to relate using these two graphs. Now, here we see that what is amplitude? This is the line of normal density, and the deviation from this line in the upward or the downward direction, this is known as the amplitude of the sound wave. So, if the amplitude is less, then it will be a soft sound, and if we increase the amplitude, then it will be a louder sound. So, we can say that the loudness of the sound depends on amplitude, and it is directly proportional to amplitude. More will be the amplitude, the louder the sound will be. So, this is the first characteristic of sound, that is the loudness, right? The soft sound or the loud sound. And on which factor does it depend? It depends on the amplitude. Clear to all? Now, the second characteristic that we will be taking is the pitch of the sound. Now, what exactly is meant by pitch? A man and a woman, they both are talking, they are saying something with the same loudness, but we can differentiate between the sound of a male and the sound of a female. And what exactly is the reason why we are able to differentiate it? Because of this characteristic, that is the pitch of the sound. Now, what exactly is the pitch and how exactly it depends on what factor, that we will see. The pitch of the sound is that quality of sound. These are qualitative characteristics, right? We are talking about the quality of the sound. Okay. So, the qualitative characteristic of pitch, it depends on the frequency of the sound wave. Now, frequency, as we have already studied, it is the number of waves they are being produced per second, right? Let us take an example with the help of once again this particular graph. Now, in first graph, you see that the waves are being produced, right? And in this particular time period, there are two complete waves being produced, right, in a particular time frame. Now, if talking about the second example, we see that in the same graph, the time amount remains same, but now the number of waves being produced are 8. So, this will be a low pitch sound and this will be a high pitch sound. That means the pitch is directly proportional to the frequency. More will be the frequency, more will be the higher will be the pitch. Right? In other ways, if we talk about, in other sense, when we talk about, the more the number of waves produced per second, the higher will be the pitch. Got it? Fine. Now there is another qualitative characteristic, and that is actually timbre. It is written as BRE. You can call it timbre also. Now what is exactly this timbre? This is the quality of the sound wave. Two people, whether they are two males or two females, they are talking with the same loudness, they are talking with the same pitch, but still we can recognize and differentiate between two sounds. One sound may be pleasant to our ears and the another may be unpleasant. One is maybe of a very famous singer and the another is just a normal person like you and me who can't sing. So there must be some difference between these two sounds, and that is the quality or timbre of the sound wave. Now what exactly is this quality and timbre dependent upon? Let us take an example once again. If we are talking about two musical instruments, one we take to be flute and one we take to be violin. We can differentiate between these two easily, whether a flute is being played or a violin is being played. How? The loudness is same, means the amplitude is same, the pitch, that means the frequency is same, but quality, and what exactly is quality dependent on? This is dependent on the shape of sound wave. What exactly is the shape of the sound wave formed? Right? Let us take an example comparing the two of flute and violin. Example, this is the time period, will take equivalent. This is the amplitude, will take equivalent up and down also. Now the shape of the sound wave may be of the flute is like this, right, and the shape of the violin is probably, just taking an example, to be like this. Now we see that the amplitude, that is the main deviation from the line of normal density, that is same in both the cases, and the same frequency is there, but because of the change in shape of the sound waves, the quality will be different. So this is the characteristic property due to which we can differentiate between two sounds, even though they are same pitch sound, even though they are having the same loudness. But if the room is dark and somebody is calling me, I can make out just with the quality of the sound wave as to who is he or she, and I recognize the voice or not. I can differentiate between them. Got it? So these are the characteristics of sound waves.